So aromatic rings reacting oddly. So we've got a couple interesting reactions that I would like you to take a look at, spend a second, figure out what type of reaction occurred, why these reactions might be weird, and then what traits do they have in common, what traits are not similar. So spend a second to kind of look at this. You can either pause the video or let it play out for a little bit. I'm just going to stare creepily at the camera because that's what I do. Hopefully you've had a second here to think about it. If we take a look at both sets, these are both doing substitutions. So hopefully you can see that. We're in the first one, we're getting rid of a bromine and we're replacing it with OH. And the second one, we're getting rid of chlorine and we're replacing it with NH2. Why are these reactions weird? Well, aromatic rings shouldn't react like this. So what we've seen so far is that we can reduce them, we can oxidize them, and even the oxidation, we're oxidizing the carbon next to it, the benzylic position. And then we can do a bunch of substitutions, but with hydrogen. Here we're doing a substitution with a halogen, and that seems a bit odd. That would be akin to kind of SN1 or SN2, but as we learned in first semester, aromatic rings don't do SN1 and SN2 reactions, so that's kind of weird. What do they have in common? Well, they are both starting with halogens, and they're both adding a very electronegative element, be it oxygen or nitrogen. We could potentially make the assumption that maybe others react, but that's not the case. That's it. We're either doing oxygen or we're doing the nitrogen. Either as OH or as NH2. And the trait that's not really similar, which would double tag on the weird, is that in the second one, we're getting the NH2 doing a parent substitution at a different spot. We might go through and say, well, it's a substitution for hydrogen. We can't really say that, though, because the number of hydrogens in both cases are the same, and the chlorine's the only thing that's not there anymore. So these are kind of interesting reactions and a little bit odd and bizarre. So let's take a little bit of a closer look. Okay. Both cases, we're looking at a strong nucleophile base, hydroxide or amide. The top case, it's a deactivated ring. We've got the nitro on there. Again, we don't know anything about this yet, so we don't know if that's necessary or not. The bottom one is a mildly activated ring. Okay, so this is kind of interesting. Let's see where this goes. Okay, what this is pushing into is a new mechanism for aromatic rings, and it's called a nucleophilic aromatic substitution. In the electrophilic aromatic substitution, the ring acted as a nucleophile reacting with an electrophile. Nucleophilic aromatic substitution is the ring is now going to react with a nucleophile. That's a little bit weird because then that means the ring must be an electrophile. So it has to be somehow accepting electrons. So that's a bit odd. Pushing into kind of the things that allow this to happen. It has to be an electron poor ring. Okay, well, why? Well, what did we say the ring acted as? The ring acted as an electrophile. The only way to be an electrophile is if you're electron poor. The only way to get a ring electron poor is to have deactivating groups around it, hence the nitro. Okay? There has to be a good leaving group. So we're looking at our halogens, bromine, chlorine, iodine. Those need to be there, and we'll see why. That's what's allowing for that substitution. And then the next part is the leaving group has to be positioned ortho or para to the withdrawing group. So remember, benzene rings have that resonance of electron density all the way around. Just like in EAS, NAS does have that resonance contribution, and we have to be able to stabilize certain intermediates and structures along that route. That's really going to have this kind of specificity of location. That's why we have to have this ortho or para to the withdrawing group, because somehow or another, that withdrawing group is helping to pull electron density away to help activate that leaving group position for a nucleophile attack. Okay, to really see that, we're going to have to dig into the mechanism. Okay, so some NAS examples. If we tried to go through and look at these two experiments, all that's really changed is we've changed the location of the nitro relative to the halogen. And in one case, it's para, and in the other case, it's meta. The meta one didn't actually work, and so that one's a bit misleading because it looks like there's a product there, but there isn't. Okay, so here we're looking at that para substitution, and here we're looking at the meta. So how might this go? Well, let's take a look and see what that electron withdrawing group is potentially doing to the structure. That electron withdrawing group can pull electron density out of the structure, putting a bromine up, leaving our bromine there. We could continue to do resonance, and what we might note is that we could get the system where we had a positive charge at that position. Why might that be useful? Well, what's floating around in solution is that stupidly strong nucleophile or base that can come in, do our actual substitution or our addition. There's our NO2, double, double, bromine. There's our new bond to the OH. Okay, we've lost aromaticity, so what can end up happening is that those electrons can swing back down and eject the leaving group of bromide. Because bromide is more stable than the hydroxide, we see a slight favoring for the final product where we've done the substitution. Okay. Some of you may remember that we said that you shouldn't be drawing resonance structures to start a mechanism. You can use resonance to explain intermediates, but here we're showing resonance to start the mechanism. Okay? So we could switch this up, and really the only reason I drew those was so that we could start to see some of that stability. Okay? I'm going to back away off the products because we already have the product shown up there. And if we went through and did the meta one similarly, and actually I'm going to stepwise that. Let's do the meta one. Bromine, double bond, NO2, double bond, positive. Forgot how I wanted to draw it as far as coloring goes. And if we go through and look at the result with the meta substitution, is that we never put the positive charge where that leaving group is located. The electrons are going to constantly shuttle around, but they will never fall in a system where we get that positive charge at the leaving group. That becomes important because the whole point is that the nucleophile can come in, and when we restore aromaticity, we can eject the bromine as a leaving group. If the bromine is never at a position where it can act as a leaving group, then the substitution doesn't happen. Okay? So it is that kind of clutch resonance structure where our hydroxide came in that's driving this. We'll see that appear in the para and the ortho substitutions. Okay? Para and ortho leaving group to withdrawing group. If it's in the meta, we'll never get that proper alignment, which means that carbon doesn't become electrophilic enough, which then means the hydroxide can't come in and nucleophilically attack. Okay? What happened was this is I would bet someone accidentally stumbled across this. They didn't expect it to actually happen, but then it did. Once it has happened, well, now it's like, well, why did that happen? And what we might try and do is switch it up to different conditions. So if we try NaOH and a little bit of heat, we don't get a reaction. If we try NaOH and a lot of heat, 350 degrees Celsius, we do end up seeing this reaction happen. Okay, well, could I modify this? Do I need such a stupidly strong base or heat, or not base, nucleophile? So let's switch it up. What if I use a stronger nucleophile can I back away from the heat? And sure enough, when we switch it up to NH2, we can get it to work, and it works with a little bit more efficiency. Okay, so NH3 liquid, we're getting pretty darn cold, so we actually didn't need the deactivated ring. But when we go through and run that reaction, what we end up seeing is a second product come out. Okay, and that second product didn't exist with the sodium hydroxide. So there's a now shift in the mechanism. Something's going on that could alter how this is happening. Okay, how is that happening? Well, the NaNH2 is not only a strong nucleophile, it is also a strong base. And we might say, well, why does that really matter? Well, if it's a strong base, it can act as a base. And what it can do, and I know this is going to look stupid, but that's okay. We have that leaving group of the chlorine, and we could go through and do just a standard elimination. Ta-da, standard elimination, and that's it. But what looks weird about that is that we now have a triple bond within the ring. All sorts of geometries are screaming like, that doesn't make any bloody sense. Why would that happen? But let's hold. It's going to want to break open. So what it could go through and do is it could break open and it could pick up hydrogen from our NH3. When it picks up that hydrogen could go to either position, or I guess technically and, our hydrogen could go to the other position. Well, what's left over? Well, we still have the double bond, which we didn't react, and then we would still have, or now we would have, a positive charge chilling out in there. Well, NH2, being that strong nucleophile, could come in and react at either spot, getting us, of course I aligned this horribly, both of those products. Right? Well, that would explain it, but that means we formed a triple bond in an aromatic ring. There's no way in hell we could possibly ever form a triple bond in an aromatic ring. That just doesn't make sense. Right? So somebody went through and said, okay, let's just label it. Maybe there's something bizarre going on behind it. So they went through and they radio labeled the experiment so that you could identify those spots. And sure enough, they noted that this was persistent. Right? And really that benzyne intermediate is the only thing that really makes sense. We're getting chemistry at those two positions. The only way those positions become active is if there's electrons between them. They're equally active. That means it must be an active alkene, right? Or alkene, an active pi bond. Right? And that is bizarre. And the best explanation we can come up with is this thing known as a benzyne intermediate. Okay? It gets all sorts of bizarre, strange chemistry coming out of it. Okay? That carbon of the triple bond there has to be sp hybridized. We're getting very bizarre bond angles out of it. There are no hydrogens at those two positions. Okay, there are other arguments that it's not really a formal another pi bond because of those bond angles, but it's a diradical. So you get a bunch of different kind of comparisons coming out of this. But ultimately, the best depiction we can draw is the benzyne as far as the Lewis structure. And so you will see test questions pushing towards this benzyne. Okay. Big red flags, amide, sodium amide. That is because it needs to be a stupidly strong base to be able to activate this reaction to get it to go through and happen. We do need the presence of that leaving group. And then look, are you seeing a weird kind of substitution? Okay. Is there other evidence that this thing actually happens? Well, sure enough, Diels-Alder reactions actually happen. Okay. We maintain aromaticity of the benzene structure in the product, which means there had to be another double bond present to act as a dienophile. It had to happen. And that's kind of bizarre and interesting. We could look at other standard reactions, HBr, Br2. A lot of those potential issues pop up because they can react in other fashions. For instance, Br2 can do an EAS reaction with the ring without it actually going through a benzyne intermediate. So we have to be a little bit careful with what reagents we can test to see that this exists. The Diels-Alder just ends up being kind of the spot-on perfect one for it. Okay, that seemed to go a lot faster than I wanted, but that's where we're at. So this really introduces two new reactions. We get what's known as the NAS mechanism, the nucleophilic. Sorry, I'm going to step back through. Come on, wow. Really didn't emphasize when I wanted to. The NAS aromatic, nucleophilic aromatic substitution. You need an electron withdrawing group, you need a halogen leaving group, and then you're looking at hydroxide. The sodium amide is a maybe because you could run it through an NAS mechanism, though when you're seeing the sodium amide, that's pushing to the next mechanism, and that's really moving to what's known as the elimination-addition, formation of the benzyne intermediate, then doing an addition with it. Okay. And so those are the last two kind of weird reactions. They're usually one-off reactions if they're tested on at all. And the primary reason for them is they're just weird. They just do bizarre and interesting chemistry. And bizarre and interesting chemistry tends to make it into exams. Okay. With that, we are done with aromatic rings. Actually, I'm now freaking out a little bit. I'm not sure that's true. Let's make sure. Yes. We are done with aromatic rings, so what we're going to move to in our very last video is a quick overview of polymers and how they can form, but that's it. We are pretty much done with the semester. So, thanks for listening. Hope you have a good day.